So we are going to use this fact repeatedly in this lecture. So this kt, this is a unique factorization domain, and therefore it is integrally closed in its field of fractions. So this is going to be the normalization of all the examples we are going to cover in this lecture. So first example is normalization of this ring A, which is kxy, and you have this ideal y cube minus x5. So we put this as an ideal I. So this we can write it as k small x and small y, where this small x is x modulo the ideal and y is this capital Y modulo this ideal. So first thing to notice is that this ring is not normal. So this is not normal. So we are going to work with this ideal and construct an equation. So you have y cube is equal to x5, so that would be y over x cube is equal to x square. So you see this y by x, this is not in this ring. So this y over x, this is not in this ring, but it satisfies this equation t cube minus x square is equal to 0 with the coefficients from this ring A. So this ring A, so you can see this x is lying in this ring, so it is a coefficient, and so this is a polynomial. And instead of t, if we plug in y by x, you can see this relationship, so it satisfies this. So y by x, which does not lie in A, satisfies such an equation, and therefore A is not normal. We have an element which is integral over A, but it is not lying in A. So now we have to find the normalization of A. So the first thing we do is we construct a map, so kxy to kt, where x gets mapped to t cube. So ideally we want this equation to give us the map, but here if we put x equals to t3 by 2, that introduces square roots which we want to avoid. So we are just going to plug in x as t cube. So x as t cube and y as t5, or you can directly see from here. So that will give you y cube minus x5 is precisely t to the power of 15 minus t to the power of 15, which will become 0 in k of t. So we have this equality here. So kxy, you modulo this, you get k t cube and t5. So instead of this x, we are going to write t cube, and y we are going to write t5, because this y cube minus x5 will become 0 in this ring because of our mapping. So first notice that t is integral over this ring. So because we always have this polynomial, this capital T cube minus small t cube. So this t cube comes from this ring right here, and we are considering this polynomial in this ring, and you are joined it to t. Or you could have also considered the polynomial this t5 minus t5. This comes from this, but this kt cube comma kt5, this lies within kt, and this is integrally closed. So this is the normalization of our ring, because our element t lies within this ring. So coming back to our ring, you can say, okay, we can adjoin t back to our ring to make it integrally closed. So you have kt cube t5 t, which you can write as kxy, and t you can compute from here. You can see that x over y is nothing but 1 over t square. So you can solve this. You get t is square root of y by x. So now we again use the same example and have identical algorithm for normalization. So now we have normalization of this ring A with kxy over y square minus x cube, and this is the ideal. And we write it as kxy, where small x is capital X modulo our ideal, and y is capital Y modulo the ideal. So this is the ideal I. Now again, A is not normal. You can see using this equation, you can say that y square is equal to x cube. So you have y by x square is equal to x. So this equation we write it in this format. So t square minus x is equal to 0, and this y by x satisfies this equation. Basically just this equation is here, but y by x does not lie here. So this y over x, this is a fraction, this is not an element of kxy. So for normalization, therefore we have to construct a map. So A is not normal. precisely because we have this element y by x which does not lie in a but satisfies such a monic polynomial. So it is integral over a but does not lie in a. So therefore a is not normal. So for the construction of the map, we have kxy to kt. Again, x goes to t square. That you can see from here. You can solve this. X is t square. So we'll use this here. X is t square, and using this relationship here, you can say y is t cube. Again, if you do y square minus x cube, you will get t6 minus t6 is 0. So you get this relationship kxy modulo out with the ideal y square minus x cube. You get k t square t cube. Now again, t is integral over this ring, so you can construct a polynomial in this ring by joining t to it by considering this polynomial t cube minus t cube, with this t cube coming from here. Or you could say t square minus t square, where this t square is just a coefficient or just a constant coming from this ring. So t is integral over this ring, and obviously t does not lie in this ring. So kt square comma t cube lies within kt. This is integrally closed, and this is the normalization of this ring. Now say we want to come back to a ring, then we have to join t back to it. T square t cube t. So t square is just our x, t cube just y, and t is y over x. As you can see that y over x is just t. So you can say this is the normalized ring. Obviously this small x is nothing but capital X modulo I, and the small y is nothing but capital Y modulo I, where I is our ideal. So notice the difference. You have square root of y over x here, and you have y over x here, and the square root precisely comes from here because you have to write x as t to the power of 3 by 2. You have to introduce some square root here, and there is no square root here, and therefore that is avoided. So another example is normalization of this ring A is kxy over this ideal y square minus x cube. This you put it as ideal I. This you write as k small x small y, where x is capital X modulo this ideal, and the small y is capital Y modulo this ideal. Now again, A is not normal because this y by x does not lie in A, and it satisfies such an equation. And this equation again comes from this ideal. You have y square is equal to x square plus x cube, which is equal to x square times so I'm taking x common from here, so this factor I'm writing first, x plus 1. So this is x square x cube, so x cube is here. So you have y by x square is equal to x plus 1. So this we are writing as t square. So you have t square minus x minus 1. So obviously you plug in y by x here, it satisfies this equation, and the coefficients, this x is taken from here. So ring is this at. So A is not normal because y by x does not lie in A, but it satisfies a monic polynomial like this. Now we construct a map for normalization. Again, kxy to kt, x goes to t square minus 1. So this thing comes just from here. So you take x from this side, you get t square minus 1, and then you plug it in this relationship right here to calculate y. So y would be t cube minus t. So kxy modulo ideal I, you get k t square minus 1 t cube minus t. So just copying this down. Now again, t is integral over this ring. So because you can have a polynomial like this, t cube minus t cube minus t. So this t cube minus t is coming right here from here. So now you can plug in t here, small t here, then this t is integral over this ring. So to have integral closure of this ring, we have to incorporate this element t. So t square minus 1 t cube minus t, this will lie in kt, and this we have seen is integrally closed. So this is the normalized ring because you have to have t in the ring. So that is it. So if you want to come back to the ring, you have to join this t to it. So again you will have t square. So here you can write this t square as t square minus 1, this t cube, we should write t cube minus t. So this is t cube minus t, second parameter. First parameter is t square minus 1, and then you join t to it. So this will be k xy y by x. Again you can see y by x is t cube minus t over t square minus 1, and now you just take t common. So you have t square minus 1 in the numerator, which will cancel with the denominator. So this is the normalized ring. Again, you have small x, small y, and y by x. This small x comes from here, capital X modulo I, and this small y again comes from here, capital Y modulo I, from this ring. Now we end this lecture with a very important remark, and you can find this in Dummett and Foote on page 729, second edition. So an irreducible affine curve, say V, and it will have a coordinate ring KV, and if this K is algebraically closed, then this curve is smooth in the sense of finding the dimension of the tangent space. So this curve is smooth, so this is geometry if and only if this KV is integrally closed, and this we saw in algebra just now. So none of the three rings which we discussed were integrally closed. So none of the curves defined by this equation or the other two are smooth. So this curve y square minus x cube equals to 0, this is not smooth. And similarly for the other two curves, they are also not smooth because their coordinate ring of this curve is this, and we have seen that this is not integrally closed. We have to actually extend it to make it integrally closed. So this is not smooth, and you can do this directly by using computing the tangent space and finding the place where the dimension is jumping, or you can find the singular points.